Okay, sorry about that, guys. Sorry about that, guys. No, that was totally my fault. The front USB ports on my machine are a bit touchy. And what happens sometimes if I don't have the USB plug the right way as I kind of put it in there, it seems to short something, and my whole machine starts up or reboots. It's horrible. Normally I plug stuff in before I start the stream because of this. But yeah, it's really dumb. What I need to do is just I need to get more hubs. This actually doesn't happen that often. Like 4 times since I bought this machine or something. It's enough to know about it. The most thing I'm worried about is the recording, but it's fine. Exactly, G Superlin. Oh, you're gonna implement a risc-v CPU as well? Well, you'd probably do it better, Volkinson. I'm just going for like pretty much the simplest implementation you could do. Like I'm avoiding pipelining and stuff for the first implementation as well. Stuff I would love to get to later, but for an initial implementation, I just don't care. Anyway, reason I wanted to bring this up. I'm gonna pop open Quartus here. And we'll move my windows around and stuff. All right. So I did a couple test projects before starting on this. Because before we get into anything interesting, we need memory. So I went through and set up the DDR3 stuff on my board. And I just wanted to talk about that and show that a bit. So that's opening. Yeah. So there isn't much here. I have a generated DDR3 interface. Let me see if I can just open that up. You go through this wizard. Boy, is it magical. And you get some IP that drives memory. By the way, when they say mega wizard, they are not kidding. This is disgusting. But essentially, you set up the speed of the memory, a bunch of the parameters like the timing parameters, drive strength, timing between that, and like based on the board, board settings, controller settings, stuff. This is just parameters for the controller. Like I have it so that it has a command queue of depth 10 and enables reordering those, which will help us with performance later. But right now, it doesn't matter. Anyway, we get to generate that interface, and then we get this stuff. And the really important part is that it has this DDR3 interface module available to us. It takes a PLL, has some other outputs about whether or not its initialization was successful, because it does some calibration when it starts up. There's some temperature sensitive stuff with DDR memory. And then it exposes this Avalon interface, which is the interface that we're going to actually use. This is the interconnect between the IP and the actual memory itself. And then there's some more stuff about clocks in the PLL and whatnot. We don't care about a lot of this, actually. I can show you how I have this set up, which might be really wrong, but it totally works. This is my top level thing. And so I get onto this clock. I take the clock from this AFI clock, because we're going to run the rest of the system on the same clock that the interface that the memory exposes gives us. So that'll be a 150 megahertz clock. Just take the soft reset to 1, because we'll never use that. Set up global reset in the PLL stuff. Map out the memory pins to the actual memory on the board. And then, take our calibration signals and our AVL signals, our Avalon signals, and then just get wires to those. Then we hook those up to our test here. And the test I have here is super basic. Can I zoom in here? No, I actually can't do that with that key combination, at least. All right, I'm not going to dig in settings too much here. But our test here takes, reset and clock our Avalon interface and the calibration input stuff, and then we'll output a couple LEDs for signals. Oh, control mouse wheel might work. Nope. That just scrolls. Worth a shot. Anyway. With super basic 2-process style, I just wrote this state machine here. So we've got an init state where it just waits for the memory interface itself to be initialized. We've got an error state and a finish state. So finish is when we're done with our test, and then error is if something goes wrong. Then we're going to set up a write and then wait for the write to be completed, and then we're also going to wait for a read to be completed. There's only one state for this instead of, like, we have one to set up the write and then to wait for the write. But the wait for the write will also set up the read, so that's why there's only one state there. So it's very simple. We wait for the init to be done, so we just sit here and do nothing until this init signal is asserted, and then we're going to move to the next state. But we check if it was a success or failure, so we'll go to the error state here if that doesn't work. So the error state basically does nothing except it updates the LEDs on my board. I have it so that the LEDs are either just going to blink all on or off if there's an error, or if it's finished, it'll just do a counter pattern, because it's like angry blink and happy blink, which is motivating for me. So it goes to the test write, and then it just sets up all the stuff for the Avalon interface. We're just doing a burst read of one word. And then, so that's dead fabe babe beef dead babe, XOR with the test counter. So I think I have a test counter here that does a full 24 bits of the word addresses, which is our entire address space. So we're going to test. We're going to go for every word that we have, and then test that it works with our little interface implementation here. So we do a write with something including the test counter, and also the address has a test counter. In fact, this is kind of dumb that I have 24 in this, but that's just remnants from how I wrote this, because it initially didn't have these. Because that should be necessary anymore. Anyway, we write all that, just do burst reads of one word, and then wait for that to work, because the Avalon interface can say it's not ready, and then we need to keep asserting the write until it says it's ready. Then we move on to the next state, and we just sit there and wait. And then when it's done, we'll wait here for the write to have been accepted by what we need to watch for at least. And then when it has been accepted, we'll send out the read, and then we'll sit there and wait for that to be finished. When that's done, we'll either go to the finished state if everything worked and our test counter was finished. Otherwise, we increment our test counter and then go to the write state again and start over. I don't know if 60 FPS is the default on OBS. I've been streaming 60 FPS since I was streaming Super Nintendo stuff, and I've just forgot to set it back, and not enough people have complained. I'll answer some of these questions in order. G-Super terminology question, since you're rusty. I know the system would be considered a unified memory architecture, but is that because of it only having one bus, or because it only has one set of system memory? I would call it a UMA. Maybe I'm wrong for doing that, but I'm assuming that's because it's one memory and everything will use that same memory. So I'm not sure if it's the bus or the memory itself that determines whether or not it is unified memory architecture, but it certainly seems that way in the way that we're going to be using it. Another hardware stream. Yeah, so we're building some hardware. I'll do a quick 2-minute recap. On an FPGA, I want to build a game console. It's going to consist of a handmade CPU or handmade, like so many of those terms actually have physical connotations, but our own from scratch implementation of a risc-v CPU, as well as a simple GPU, which is kind of the part I'm most excited for, but I'm also excited to learn a lot of the rest of this, how the pieces fit together. It's called xenowing because that sounds ridiculously 90s, which is definitely the kind of era of hardware that I'm targeting here, although I think I'll end up in the pretty late 90s just because of the clock speed we end up having here, and the amount of memory is pretty ridiculous in terms of those constraints, but it's the amount of memory that I have on my FPGA board. That's what I believe is 192 megabytes, but we're only going to be using 128 of it because it's mapped in such a way that there's a 16-bit word chip and there's an 8-bit word chip, so it's 24-bit words rather than 16 or 8-bit words altogether. And so I'm just going to use the lower 16 bits for the words. And because of the data rates, because it's DDR, so it's running at double data rate, and we're running that at 300 megahertz, and our interface runs at half rate from that, which means the memory is actually running at 4 times the speed of the rest of the system. Our actual word size is 4 times 16 bits, or 64 bits. But yeah, that means we're using 2/3 of the memory available, so we should have 128 megabytes of memory altogether. Okay, yeah. So if the is distinguisher the right word there? That looks so weird to me. If the determining factor, I'll say, is based on the GPU sharing CPU memory, then definitely this is unified memory architecture, because we'll do everything through this using the same memory. And there's going to be some advantages to that, mostly in simplicity. Like, I don't have to give the GPU any notion of double buffering or flipping the buffers. I can just change its buffer pointers. So that'll be cool. It pushes all those problems to software, which is kind of where I want them. Because yeah. And like in the Virtual Boy and many other systems as well, but that's where I saw it last. We're going to separate the GPU into kind of two halves as well. There's going to be a display half and a drawing half. And the display half is just pulling memory out and putting it onto the screen. That's the one we actually have to do vsync for. The drawing half is, putting pixels into memory. So, yeah, I guess distinguisher is a word. Assuming that came from a dictionary and you didn't just type that in the right form. I'll give you the benefit of the doubt. Yeah, and the last thing I have here is I just separated out the LED clock divider stuff. It's just a thing that just gives you a pulse, not an entire like the clock doesn't stay low and then stay high. It just gives you a pulse when it goes from a low to high transition at a much slower rate, and that's just so that when the LEDs blink, that I can actually see them blink during this test, rather than them just looking like they're just half on because of the PWM effect. Oh, it is G Superlin. I'm well aware of the dangers here. I think I'm too far down this road at this point. The reason I'm talking about all this memory stuff is that one of the things that we'll need to do pretty quick here is, there's a lot of pieces of this project in my head, and we kind of have to do all of them. And I could sit down and meticulously plan what we want to do, and I'd rather just kind of bang on it until it works. It's because that's what I feel like doing on my weekend. And so one of the things is we need to emulate the other side of this memory interface. So this assumes that you have this Avalon interface here. And this works against real hardware. I can actually show that process. In fact, we can do a signal tap thing here. So signal tap, by the way, is quite cool. I already have all this stuff set up, and in fact, this is the last session that I had. But what you do here is you have a setup and data tabs, and in the setup tab you set up all the things that you want to watch. So these are just different signals. Basically, almost all the signals in that test thing. There's a couple things that are wrong here, like that is an old state, so that doesn't really make any sense anymore. There's a couple other states I could add, but I just don't care. And then so I'm watching all these, and one of these I set as the trigger condition, which is when this DDR3 init done goes from low to high, then we start watching all these other signals. From there, it's a basic logic analyzer. I can set sample depth, set which clock it's going to be looking at stuff. So it's basically adding a signal analyzer into the design alongside the design that I already have. And this allows me to actually watch what's going on the actual hardware. I needed to use this to get the interface to work because I had initially implemented the Avalon master wrong. So my initial read tests would do one write and read cycle that was correct, and then they wouldn't be able to do any more. But now it's fixed. So when you start this, then you do this compile thing. I can't do rapid recompile. I think that must be a standard or pro feature. In Light, I can't do that, so I have to compile everything. But yeah, this is going to compile. Compilation for this stuff takes a long time, by the way, which is one of the reasons why we want to use a mostly simulation-based workflow. It's going to take 3 or 4 minutes here, just waiting for this. But it's cool to see it like actually happen. Even though I'll just be pushing buttons on the hardware on the side, it won't really matter. You guys will see what you need to see. I have a second camera here, but I just don't want to set it up. Gotta adjust a bunch of like exposure settings on it and crap too, because it's all calibrated for staring into the Virtual Boy right now. And I don't want to adjust all that. Anyway, the different stages here, it's gonna like analyze and synthesize. So it's gonna basically create a net list of my code, a list of gates and their interconnections, based on the pieces of Verilog that I have here. And whatever else. I think this takes about half the time. Then the place and route's going to take about half the time, and then the rest is a lot faster the way I have this set up right now. But yeah, most of the time goes to these two. So maybe 45% of the time goes to either one of these. This is what it seems like. I could also be completely wrong about that, but so yeah, so that's going to happen. And there's actually some really cool stuff that happens after this that we can look at while it's doing the place and route. So once it has the net list, the list of gates that we have in our design, then it's going to actually figure out where those are going to be implemented inside the chip, and that's what this place and route's doing. After that, it's just going to assemble that into a bit stream that it can send to the FPGA, and then it's going to do some timing analysis on the final bit stream. I don't actually know why these are in that order, but that's how it is. Yeah. Come from the Rust community these days, so it's not like I'm not used to bad compile times. No, it's definitely worse. Supposedly this is faster if I want to shell out a few $1,000s for a proper license, but that's not going to happen. But I thought I could show you some of this report stuff, but I guess I gotta wait for the entire compilation to finish. So we're gonna sit here and wait. One of the nice things though about these compile times is that, like, when I was iterating on this interface, I was looking at the signals as I was iterating and just saying, okay, what if I try this? What if I try this? And I had another working implementation that was like a generated example project for this memory interface, so I could compare the two. But while it was compiling like this, I just watched TV or something, so it's not that bad. Thanks for the bit, Mortaray. Appreciate it. Hey, Dark Second. Yeah, if it turns out I end up doing a lot of hardware stuff in the future after learning some of these skills, that would totally be a great place for stream money to go to, even though I don't make nearly that much. But it's very much appreciated, so thank you guys for that. Yep. Yeah, so the place and route, as you can see, is actually a lot longer than I thought compared to analysis and synthesis. But that makes sense, though. I mean, this is a compiler, and this is a heuristic machine. So just being on the FPGA, you can tend to be pretty blind, but the fact that I'm using this signal tap thing actually really helps here. Like a lot. So that makes us a lot less blind. There are other peripherals on the board though than just the memory, like the HDMI interface, for example. We need to sort of emulate and abstract that. In terms of the development parts, I'm not really sure how to answer that question. I guess you're more looking for like big hurdles that we'll have to go over, or just general challenges. I mean, the fact that I've never done this before is kind of a challenge, but yeah, I need to set up my setup here for the JTAG, and then I can, okay, so things have been built now, and I can put this thing on the device now. And now we're ready to acquire, so I can hit this button here, and now it's waiting for the thing to acquire data. So I'm going to hold the reset line on my device. There's a button for that, and when I let go, it just acquired all that data. And it's actually still working. It takes like 4 to 5 seconds for it to hit the entire address space, because when it's just doing reads writes like this alternating, it's actually super bad for bandwidth, because it's got to open and close a bunch of rows. Even though it's the same row, I think it's not that great of an implementation, but probably better than I would do, at least on the first try. Anyway, you can see here was our trigger condition when the DDR3 was done being initialized, and we can zoom in here. So when that was done, then we started. Here's my burst begin signal. So I do a write here. I request a write with the data, and then right after that I do a read, and I just do bursts of byte 1 or length 1, because that's just the easiest thing to do. And then sometime later, data valid comes back and says, "Hey, I got your data." And then I just do the same thing again. So it's super basic test, and it totally works. So one of the things that we're going to want to do in order to move this to simulation, now that I know how this interface works, we're going to implement an emulator for this controller IP in Rust, and set all that stuff up so that when we're simulating in the Verilator simulator, we actually have some memory to use. That's the idea there anyway. And we'll be doing the similar things for the HDMI stuff. Although that's actually a lot simpler. There's a I2C bus that we communicate with it over to set a couple registers. And I actually hope to memory map all that stuff. And then do that through here even, because I think that'll be a little easier. And again, we can push a lot of those problems over to software, which is where I think some of that stuff belongs. Like if we give it a basic serial interface in order to allow it to run that I2C bus and go and fetch data, and then just check what the data it fetched was and stuff. Like I think it's a bidirectional interface when you do that. But if we just set up a nice memory mapped interface for that, then we can do all the actual register setting in software. Because then I can do stuff like, detect when the HDMI cable is disconnected, because that actually disables the chip. The HDMI transmitter chip will turn itself off when that happens, and I want to detect that and then be able to turn it back on if the cable's plugged back in. And I think like that kind of logic I would just rather have in software, just because it's easier to describe such sequential logic like that. I also think that eventually I'm gonna come up with a way to just like send code over UART or something to be able to reload just the code part and not the hardware part. So again, that stuff will make a lot of sense. And I should be able to just port over the I2C stuff that I've done previously. So I think that'll make a lot of sense. All the kind of stuff we have to do before actually getting output of this from this thing. But I was thinking I would kind of start doing this now, actually. Because why not? We have to do it anyway. And there's some details about that interface too, which actually is kind of nice to show in that signal tab thing. A couple details of this interface that I want to have in my interface. So there's, I don't know if you call this a bus hierarchy or what you would call it, but that's what I would call it just off the top of my head. But there's going to be a couple things. I need paint. So we're going to have our CPU. And we're going to have our GPU. right? Now these are both going to, so the CPU is probably going to go through a couple things. I think each one of these are going to have a set of caches that they might go through. We could just do the $sign here. The CPU I might have a couple different interfaces, so we'll have some caches, and then we'll also have some MMIO, because we can kind of design this interconnect however we want. And the way that I'm thinking I'm going to do it is we'll have some connections to both of these. And there might be some other memory here too than just MMIO. But I'm basically thinking something like this. Again, I don't know what you would call this. I would call it a memory hierarchy or perhaps a bus hierarchy. And then this is going to be our DDR3. And then, yeah, instead of just MMIO here, I also want I don't know what I'll call it. We can call it fast mem. So you wouldn't need, actually that should have been here. Fix my paint diagram here. So there's this fast mem thing is not necessary, but there's a reason why I want to have it actually. There we go. So it isn't essentially iCache, although an iCache would be hooked up here. The reason why I'm thinking about having a fast mem, the main reason is that I need to get code into this whole system on startup. And the easiest way to do that on an FPGA is just to set up either some RAM or ROM, and just have it have its initial contents. I'm thinking about just doing that with RAM, because I could have like 64K or something just set aside, and then that's mapped to a certain address on memory, or a certain address range in memory. Because if I'm gonna have that anyway, and I have the option to just have that be RAM, I might as well take advantage of that. So initially it's gonna have the program in it, the initial program, what I'll call the boot ROM, but it's really going to be the boot program because it's not going to be a ROM. Yeah, so that's fast mem, and that's going to be mapped to a certain range, and then the memory map IO is going to be mapped to a certain range, and then maybe we'll have like a data cache here that's going to go out on the other stuff, and then yeah, maybe there's an iCache here. Call this an iCache. Maybe there is. I'm not sure. I would like to have this eventually, but you start to need it a lot less when your fast mem is only one cycle away, so I may not need that. There is going to be, in the CPU, we might want to have iCache and data cache out of this anyway, and it might be possible for the CPU to still access memory through the DDR3 bus, depending on that range. So essentially what I'm thinking, though, is that there's going to be some memory mapping at this level already, and it's going to map to different kinds of memory. But a big thing that this will help with is reducing contention on the DDR3 bus. Basically, most memory that the C program and stuff is going to use is going to go into here anyway, I think, just due to the way that I'm going to map stuff. So, like, this would have to be managed explicitly by the C program. Not really sure how that's going to work, but yeah. And the MMIO stuff also just doesn't need to have contention on this bus. Because, like one way I could do that is I could have this sort of inverted, where there's sort of like the bus, and then the CPU and the GPU both connect to that. And then out of this, it gets mapped to, memory mapped, DDR, and what have you down here. But then you have contention at this level all the time. And that's something we would like to avoid. This way, the GPU at least is offloaded, because the CPU is going to be fetching instructions from fast memory later, an iCache probably, but from there. So how this hierarchy of different buses and interconnects is going to work, I'm not entirely sure of. But at some point, all of this stuff is going to end up connecting to the DDR3 for both the CPU and GPU at least. No, it's not going to take a bunch of code from DDR3 into fastmem. The fastmem is going to be normally like initialized on FPGA startup. So this is just some memory. And then if you want to work out of this, you have to put memory from the DDR3 into this, or generate some memory into this and then use it however you please. But I'm thinking right now that the initial program is going to be so small that that's not going to matter. Like 64K is going to be a pretty good limit for this, I'm thinking. And that won't take up too much of our internal chip memory. Now, later, of course, if I wanted to extend the system, like if this were a proper system, we would also need some kind of storage. And then the memory mapped interface would be connected to, disk or something. And then maybe we'd want some kind of DMA here. It depends. But yeah, it's going to be the fast. I'm calling it fastmem because it's going to be general purpose enough that it could make sense to have scratch pages. But it's really kind of a consequence of this is the easiest way that there is to get code into the system, is to have RAM or ROM that's pre-initialized, and might as well make it RAM because it doesn't really change our design much. The thing is that I'm kind of interested in how a lot of these pieces fit together. Like I'm interested in this part here. So, and I don't really care that stuff like this is error appropriate. Like, part of this design is going to be influenced by the fact that we're doing this on FPGA right now. So, I think this is an okay design. Anyway, so we could just implement the CPU. So there's an important thing here. We could just implement the CPU against the fast memory initially, and then it wouldn't really be a problem, except that the CPU generally, especially the data path, needs to know that it won't necessarily get bytes right away. And if I just code it against the fast mem, I don't want to code myself into a corner there. Because like if it is going to read from DDR3, it has to stall until it gets the data back, which, as we saw from here, can take several cycles. Like from my read request to when I get the data, this is like 40 cycles. Like it looks like it's about, yeah. Go from 4 to 52. So yeah, it's about 48 cycles that we have to wait. And I don't know how stable that is. But that's how long, like it can take an arbitrary amount of time. And it could even be that this data ready thing could be, it's normally high, but then if it ever goes low, we have to stop doing what we're doing, stop dispatching. But yes, Vogensen, that's exactly what I'm thinking of. Is that I want to essentially copy the Avalon design, but just parts that we need. Like I'm gonna remove bursts and stuff, for example, because it's gonna simplify things. Just everything here at this level is just gonna be implemented with one word bursts. So we have like word reads and writes, but then I'm gonna copy this data ready signal or this ready signal, so that like for example, if the CPU gets through the cache or whatever, and then does actually need to do a read or write on the DDR3, and it's at the same time that the GPU needs to do a read or write on here, we need some kind of interface between here at this level, which is going to arbitrate that. And also be aware that the Avalon, it also needs to be aware that the Avalon interface can also not be ready. So those signals have to bubble back up as well. The Avalon interface it's interface standard from Altera, or now Intel, and it just happens to be the interface that the generated memory controller IP gave us, and that's what I'm implementing here. All these are the signals that I'm spitting out to interact with this Avalon interface, and then get data to and from there. Yeah, that clock is 150 megahertz. So yeah, that would be 320 nanoseconds for the word, and then the word is 64 bits wide. Technically, this word is 96 bits wide, but we're only going to use 64 bits of that, which is slightly wasteful, but but it's going to give us more than what we need, and it's going to simplify address decoding. So That should be good. And that's also the first one. You can see here, most of them are actually faster. But I think out here, something happens and then it all of a sudden goes really slow again. I don't really know what happened there, but it really just goes to show us again that we can't rely on the timing there. Except that we can understand that, like, we can use this to roughly consider how far in the future our video memory interface is going to have to read, for example. So I haven't done that math that you just did, for example, so haven't looked at how fast that is. I'm just assuming that this will all be fast enough because DDR3 is fast. And the only resolution I'm pushing out of this, or that I plan to push out of this for now, is going to be 640 by 480. And it's HDMI, so that's progressive scan. So yeah, so with this test, I've implemented like a super basic implementation of a master of this interface, and I need to emulate a slave that actually has memory in it. Yeah, I thought it'd be the right resolution. It's also very simple because I think you need a 25 megahertz clock to drive it, which is very easily achieved based on our 150 megahertz clock. But yeah, so we're gonna have to make our own memory interface, and I want to have this this emulated memory set up before doing that, so that we can kind of make sure that this works. So what I would like to do is, yeah, exactly, G Superland. Exactly. So I would like to port over this test here and actually use the same Verilog test file to test against our emulated interface. So that's something we'll want to do here as well. And that will, again, just test our emulated Avalon implementation, but then that's what's going to allow us to, in the simulation environment, start building our own memory interface on top of that. So that's why I want to do this so early. So it's kind of jumping back and forth a bit from, yeah, we just did an ALU, and that's only part of the CPU, but it's going to be a lot easier to test the rest of the CPU once we have a memory interface and can actually give it bytes, even if it goes through this interface that doesn't need to be this complicated yet. I just think by the time we have the CPU starting to read bytes, if it's reading through a full interface rather than something that we're going to have to change later, I just think overall this is going to be an easier way to go about it. Plus, this memory interface stuff is pretty fresh in my head right now, so it's kind of also a good time to get that out. Yeah, enough talking. The other thing is that I want to have these LEDs here and just come up with a way to display those on the console or something, because then that will also make this easy to test. No, I'm not actually deploying to hardware. This is my DDR test FRAM. This isn't our CPU. So I mean, I guess I did deploy something to hardware. Just probably not what you expected. But yeah, it's going to be a really good sign if this exact same test code works against our emulated thing. And that's what I'll use to test it as well. So I think this will be pretty straightforward. I need to actually do like a proper diagram of that. I still think it's called a bus hierarchy is what I'm going to keep calling it until I hear a better term for it. Because I would kind of like to have that visually while working on it later, but right now I just know that at the bottom level there's going to be an Avalon interface for DDR3. And so yeah, so like exposing the interface that we have is basically just removing burst writes from this Avalon interface and only using 64 bits of the read and write data paths. The byte enable thing it does is okay. I'm fine with that. It's only going to accept reads and writes on word boundaries. I think that's fine. I think it's more topical if it's a bus matriarchy. Ooh, that might be it. Bus topology seems to be very much a networking thing, but I mean, it's the same stuff. It's just on a synchronous clock. Maybe I'll start splashing that in there. Anyway. So what we want to set up here is a couple things. I'm going to do another thing here. I'm going to call the CPU. Stuff these in there. I'm going to do that in Explorer. Also don't need Slack open right now. I'm really slow to find the folder in Explorer right now. Okay, stuff those in there. Sublime is an idiot, so it doesn't know that these are the same. That's fine. Close this. And then we need to change a couple things here. You know, I'm thinking that this RTL thing can be part of the... Or I guess that's just where this was. Let's just keep it here. I'm just going to fix all these paths here. That probably just works as this. And it doesn't... Yeah, because of this stupid include thing. Oh, I'm not surprised. DDR3 is not simple. And the interface that you have to it depends a lot on like how the DDR3 is laid out on the board, how many individual chips you have, board timing. I don't expect our little implementation to be that bad anyway, especially because it's going to be behind the Avalon interface. So like, it's not like I have to actually implement DDR3. Really, I just want to implement some kind of interface that makes sure that it knows that you can wait. I think I'd rather implement it ourselves just for speed in the simulations case, because I don't think it'll be particularly difficult, especially since I'm kind of only really supporting a subset of it anyway. So we're gonna actually make a new folder here called sim in RTL, because there's, or actually we'll do tests here, or test, because there's some of this RTL that's only gonna make sense for like device enter tests, top level files and stuff like that. So yeah, I definitely don't need that. And it would be a lot faster if we didn't have it. I'm just going to copy this test folder. Do it here. There's a couple things I'm going to do here. First of all, if I just save this. SV. And I really don't like, it's got all this extra white space and crap in it. So I'm gonna clean some of that up. It did get my indentation correct for the places where there should have been indentation, but let's see. It should be that it should get rid of this stuff when I save. I don't know why it's not doing that. That's actually bugging the crap out of me. Yeah, I'll leave it for now. It's not terribly important. Anyway. This is totally enough for what we need. We need to emulate these calibration things. So I'm just going to have the calibration stuff happen for a while, and then it'll be done. It'll just do success for now. We could also emulate failure if we wanted to. Can make that a parameter for our emulator, but I just don't think it's going to be important. And yeah, we need to implement this Avalon stuff. Also, I think all of these regs here, I think all these become logic, which I would rather have. Same with this one, if we're going to use this stuff. And this becomes always comb. And this is going to be always FF. Fancy. Now, the other thing I think I'm going to do here, and this kind of breaks compatibility a bit with the original interface, or rather, I think what I want to do here, because these are 96-bit wide interfaces, and we know we're only going to use the lower 64 bits, so I'd rather just do that at this level, make that part of the interface, and then when we wire it up to the actual one, we could just ignore those top bits, set them all to 0. I think that's okay. And then we'll adjust the test to only test those. Also, while we're at it, I can remove a couple of these, because these aren't used, since it's going to use the full width of this for these addresses anyway. So wherever it has a 96-bit wide, we'll do 64. And we can get rid of dead babe on the end of this. So now it's dead fade babe beef. And that makes sense. And it still should test. We should still have a 24-bit word address, a 24-bit wide word address, and then a 64-bit wide word width. Again, we can do that math. 64 plus 24 is our bit width. Or sorry, that's totally wrong. 64 bits multiply by. Why am I just blanking on this math now? 64 bits divided by 8 is going to be 8 bytes wide. And then 2 to the 24th. Two to the 24th by 8. And I believe this is 128 megs. We can do divide by 1024. Divide by 1024. Yeah, 128 megabytes. Okay. That's what we expected. We're good. We're good. Yeah, it's supposed to be 2 to this plus this is how I should have done that. where we take 24 plus 64 is 88, and then 2 to the 88th. No. Why am I so bad at this? Screw it. It's 128 megs. I know it is. But yeah, so what I want to do is also make a top level file for this. So we can call this DDR3 test top. And again, I'm going to copy this thing initially. Now there's a couple things we don't need here. This global reset thing, for example, we can just call that reset n. Another thing we're going to do here, because we're not actually going to have the real DDR interface here. Because we're going to do this a little bit differently. So this also is going to have input clock. We're going to run the clock off of that, so that's not going to be wire anymore. All these wires we can make again logic, unless I'm totally doing that wrong, but I think that's going to be fine. These only need to be 64 bits wide, not 96. Most of the other stuff is the same. I'm going to actually, in our emulator, assert that we do the bursts correctly and that the bursts are only one word in length, so AVL size is 1. And that's just going to be part of the emulator, because that's a configuration that I've tested now that I know works with the hardware. So if I just assert that in the emulator, that's fine. Yeah, so we have the test itself, and then these here, instead of being logic, because they originally routed out from that original thing, we actually instead remove this interface because we don't need that, and then we're going to have these signals as part of the interface to our top level module. So this is the stuff that the emulator is going to hook up to. And then, so AVL ready becomes an input, burst begin becomes an output, the address is an output, the read data valid is an input, read data is an input, write data is an output, byte enable is output, read request is output, write request is output, and the AVL size is output. At the same time, these ones here become inputs here. Yeah, I really don't think this is too bad. Of course, now that I see this, we don't actually need a top level file because it's just the same signals. So let's just get rid of that. And that's fine. So yeah, so we can just hook up to our test directly because it's just the Avalon interface, and then also these calibration things. We're also going to use the LEDs to print to the console, which will be good enough for doing the test here. Another way to do that would be to take the state stuff, which I should probably move to an enum, but shouldn't really matter for the test. And we could expose that as well. And then we could, if we wanted to do a regression test, we could actually watch that state. So we'd run for however long, and then assert which state it ends up in. But for doing this, I think it's just going to be fine if we don't necessarily set it up as a regression test. Hey, Sir Click a lot. Yeah, if nothing else, I want these streams to show that this is accessible. If I can do it, you guys can definitely do it. Okay, so now we're going to copy some stuff here. Here we did ALU here. For this driver. So we're just going to start by making a test driver for the DDR3 test, just like we did with the ALU driver. I'm just going to copy this. And if we do this, this probably won't work right. But it should at least show us that things are running. Oh yeah, and I need to add stuff in make. For now, we'll just do make without make test. But I need to do should do the ALU test, and it'll also make the DDR3 test driver. And we got lots of errors, which is what we totally wanted. Oh yeah, this also uses LED clock divider. I'm going to copy that over. Why not? Okay, that should be good. And then we're also going to have to specify a couple other things here. This varilator thing needs to know about the clock divider file. And we have here some warning about the test should match the name. That's fine. I'll actually fix that. Yeah, now we have some warnings about widths of things. That's actually nice, I think. So we'll go ahead and fix what it tells us to fix. So this is I'll fix this first one. Our state machine here for this test doesn't cover all the cases because we only have so many states, but we use 3 bits to describe that. So there's a couple other states here. We have 0 through 5, but we also have 6 and 7 that aren't covered here. So we should actually have a default here. And all we can do there is we can do state next is state error. And that's a decent default there. That should never be a case that actually happens, but I don't mind fixing those things for mornings. So click a lot. We're making a a video game console in Verilog. Right now, working on we're gonna emulate some memory. It's an FPGA implementation, actually. It's just we're doing Danny Fritz. It's just we're doing a lot of this with simulation based tools, because that's going to be our most effective workflow. But yeah, it's actually an FPGA implementation. It'll just be a while before it gets on the FPGA, but that'll be very exciting. I'm going to do it in hardware in terms of putting it on the FPGA. I'm not going to do anything lower level than that, because there's no way. It's gonna be too much stuff. But I'll have it in a chip in the sense that it'll be on the FPGA. I do want to fix these other width ones here. So this was 89. We're exclusive ORing some stuff. Yeah, that's exactly it, Creekpot. We'll also have some of the simulation in Rust as well. So yeah, 89 here. This is this one, because the test counter here is 25 bits. But this it wants this to be 64 bits. So an easy way to do this is we can just add a bunch of zeros to the beginning of this. Concatenate these couple values here. So this will be 64 minus 25, because I'm bad at math. 39 bits wide, and then we'll just have it as zeros. I don't know if you actually need to say like hex there, but I tend to like to. So that should get rid of another error or warning. And then 121 has a similar one. Should basically be the same thing here. Hey, John Hunter. Was that really it for warnings? I thought we would have had another one. Because now we're going to have C++ issues here, and that's actually great. Episode 1 was yesterday, John Hunter. Did I? Yeah, I totally did, by the way. Nice catch. Yeah, okay, here's our warning here. Although... Okay, so now it might actually misunderstand this precedence, which should be nasty. I'm pretty sure it just got that precedence wrong, but I'm happy to have this be more explicit anyway. Okay, so now we got to go in our JR3 test driver here and set up all these signals. This VALU thing becomes VDDR3 test. So we're basically going to be simulating the test, which is a hardware been described as a piece of hardware, and we're going to emulate the memory. And this should make some sense. right, so now we need to do this more boring stuff. We're using simulation and emulation to help us build the hardware, or help us build the description of the hardware, I should say. So it's, surprise, doing hardware is a lot of software. Okay, reset N, and then we'll do set reset N here. And we just use 32 bits here, just because we do. I just want to make sure this works. This is actually GCC. We're not in Rust yet. I'm just gonna pull this down on another part of my screen so I can see the interface here. Where'd it go? This one. Here's our driver. There's our resets. We're also gonna need our clock. Oh, nice, Hunter. Need to get me one of them. So we have the clock signals. Now we need to do all these Avalon ones. These will be a bit annoying, just because there's a lot of them. But that'll be okay. I'm just making here, like, with as intermediate steps to make sure we haven't messed anything up yet. AVL ready. We'll do burst begin. Oh, it should be AVL burst begin as well. And burst begin, not with an underscore in there. Okay. So now I need the address. I'll still do this as a UN32T, even though it's going to be 24 bits. I couldn't just pass the top object into rest directly because it's going to be a C++ object, so I wouldn't be able to get the function pointers or the values that I need to call. I would at least need to wrap these in a struct. So we're stuck with that. If Verilator generated C, we'd be okay. But alas, it does not. If it generated rust, that'd be even better. But this is a relatively small amount of work, considering... Actually, we need... There we go. We could also not use rust, which I'm still open to, but I want to give it a proper go first. Doing it this way. So now we have AVLR data. Here we need UINT 64s. Yes, no need the right data. I still am playing around with doing my own HDL. I did start on that compiler, but kind of once I found out Verilator existed, it at least made sense to try it. Because I need to become a little more familiar with a lot of the tools in this space anyway. Here's our byte enable signal. Kind of a big interface, but later when we hook this stuff up, we can just copy this. So that also helps. So we need read request. We need write request. Then we're going to need size at the end. Yes, just size is the last one. That's the size of the bursts. That's what that is. So we're basically always just going to assert that that's 1. Macro would probably be fine as long as it included the type. Maybe that's better. I'm not going to refactor this, though. Now that I'm done with it. Yeah, so that works. Pretty sick. You know, another thing I could do actually eventually is generate these. I think that would actually be the right thing to do here for these drivers. Considering everything else is going to be the same. And then I could also generate the equivalent struct definition on the rest side. And it's really common when doing this kind of work to have these kind of generators, I think. For not just the test stuff, but even for the hardware itself. Or the hardware descriptions. The RTL is what I'm trying to say there. So maybe I'll consider that later. But I don't think we'll have many of these drivers. I think we'll have like 4 or 5 of them. So it's... see if it becomes enough to annoy me. But I'm not there yet. And yeah, let's just start working on the Rust project here. So one of the advantages here, one of the reasons I wanted to use Rust is because it's going to make it easier for us to pull in existing projects, like to get a frame buffer that we can just output pixels in. It's going to be easier. Also, like this DDR3 emulation that I'm going to be doing, I can make that as a separate crate, and that'll be easier to pull into the other Rust test and simulation projects as well. So it'll make it not only easier for us to get code from elsewhere, but also package up the code that we have locally in the repo. So I think that still makes sense. So we got to do a couple things now. I'm going to just do the Rust project as a separate project again. And then we'll hook it up in the make file in a minute. Oops, cargo create. Bloop. And then we'll do DDR3 test. I'll just do DDR3 dash test. That's what we'll call it. Oh, it's cargo new. I don't know why I thought create. Actually, I do, because uno create is what I use at work all the time. Okay. And then we'll just copy some stuff here. Like this. And this will be DDR3 test. And we can even copy this crap. And all this will be wrong, but we'll get there. And ALU. Just call it DDR3 test like that. And we need to do a bunch of this stuff here. This is where we need to record these same signals here. Where'd it go? What are these lib ones? Here. So I'm just going to keep the res one. Use that as the model here. Instead of results, we reset n. We need to do our clock as well. Yeah, it might make sense to separate this stuff out into different folders and have generators for generating this stuff. But I'm not going to do that now. I'll just do it by hand again. Not really that concerned about that. So maybe already again. And first begin. And then we need the address. And if I were doing this a little more carefully, I also would not have sets and resets for a lot of this, because some of these are inputs and some of them are outputs. But I don't really care. Read data valid. Then we need our read data. And again, this is going to be U64s. And then we need our write data. And then we need our byte enables, 32-bit again. That's a 32-byte again, 32-bit again. Maybe I said that right. Who knows? We need the read request. We need write request. And the size. We're also not done because there are a few things I didn't map. So I got to go back and do that, but that won't be too bad. Request, write request. And then, yeah, the size is the last thing we need. Our burst size, as it were. Yeah, because that's the whole Avalon interface, but we also have a couple additional things here that we haven't mapped, particularly the initialization stuff and the LEDs. So we'll do those next. We need init done. We need cal success. As our whether or not our calibration was successful, which I'm assuming is valid once init done is asserted. Otherwise, it wouldn't make any sense. I suppose they might happen before, but. And we need the failure one as well. And then we need the LEDs. And they're actually LEDs N because they're active low. Let's make sure I didn't. Yeah, I thought I did that. It's just LEDs N, not DDR3 LEDs N. Yeah. I think we're good there. We'll just add those to the Rust side of things. Barbarin Olve, thanks for the follow. Hope I'm reading that right. And then last, we need the LEDs. And that should be LEDs N. It's again active low. The same way that our reset was as well. Okay. First of all, this should build. Actually, it won't, because I think we have some stuff at the bottom with some errors in it, but this should still build. And indeed, the code down here is just wrong. So we will go ahead and fix that. A couple things here. I'm going to reset stuff. I think we just do dir3 test dot set reset n. It says active low. We want that to be false. I'm also going to set the clock to low as well. I might actually replace this instead of a Boolean. I might make that logic. In fact, some of this stuff we want to actually map to Booleans instead. Now that I think about it, actually this one as well. I'm just gonna fix this now because it's not gonna be too hard. We want U32s over the boundary there, but everything else we want bools. And all the other stuff, we just want the nice size that'll fit. We did a valid as well. We want booleans. Compiler should actually tell me where I messed this up now. Which would be nice. There we go. Of course, we need to change some of these too. Some of these getters here. Let's see if this works here. And it will. But yeah, a nicer abstraction might even be to use an enum for high and low rather than a Boolean, but oh, really? Oh, yeah, of course. Because I always forget this. These ones need to stay U32s because that's the boundary here. And these ones need to be bools. Maybe already as well. Burst begin. Also a Boolean address. Our data valid is going to be Boolean. Read request and write request. And then all these init done ones. Ah. So now we can set this. Of course, all this command crap is all wrong. So get rid of that. But like this should compile. And should work as well. Just shouldn't do much. Just testing this here, that this would work. Oh yeah, it hasn't built yet, so it won't work yet, but DDR3 test.dll is what it should be. Yeah, didn't segfault at least. That's a good sign. In fact, if we change this, we'll make sure that's all linking correctly at least. I expect it would. It didn't. Maybe it's not actually running this. Oh yeah, it's not. We're not testing the return type. Not doing anything with that. So this is probably fine. I'll just leave it. Anyway, this should eval here. And then we're going to set the clock to true. And we won't eval that. Maybe we will. No, sorry. Set reset negative to true. And that's going to lift that. So then simulate in a calibration, so we can just do 100 cycles. We have no idea how long this would actually take. I mean, we could measure it, but I don't think that's going to be very interesting. So we just crank out a bunch of cycles. Well, we do cal, and then we do. Oh, also, the thing is for reset, we also need to do something else here, which is resetting the lines that we actually control. So we need to set a bunch of these. For example, set init done to false because that's not done. We're going to set just reset all the values that we control here, like we would in a well-behaved hardware implementation. And then, yeah, also the other signals that we're going to assert. The LEDs we're not going to, because basically all the things that are outputs from the Avalon slave. I actually don't think they're called slaves. You have masters, and I think they're called clients in Avalon. I've got the spec on my other monitor. Nope, they are called slaves. So, yeah. All the things that the slaves are expected to drive, we need to do this. And that should be it, actually. Most of these are driven by the master, so I mean that makes sense. And we'll do another eval here, even though I don't think we need to because of this. Yeah, let's actually not. And then here. We're going to set init done. And we're going to do cal success is also true. Just say that those are successful. We could also assert that like these other things aren't crazy, like the inputs aren't crazy after this, but I'm not that concerned about that. At least not with our implementation. Have to be a bit practical here. We're going to do a couple things here now. So once this is done, Once that's done, we're moving. We'll worry about this stuff later. We're going to do our LEDs like this. Actually, we'll do it LEDs N to make that easier to match. We're going to do a couple things. So I don't know if any logic actually happens on the falling edge, so we'll do most of our stuff here. So we get a rising edge, and I want to do a couple things here. If DDR3 test dot LEDs N is not equal to LEDs N is DDR3 test dot LEDs N. So I want to output these to the console for now. So we'll get basically the same interface that I get on my FPGA in how they blink. And so what I'm going to do is I'm just going to watch for changes here. And if we get a change, we can do LEDs changed. And then we'll just do the different bits. Highest to lowest. So now it's 1, 2, 4. In fact, we need to do, if this equal to 0, it's 1, otherwise 0. Yeah. We'll do highest to lowest because that makes the most sense to me to print them that way. Yeah, it kind of matches what I can see visually. I know you guys can't see my board, but it's just 3 LEDs that are flashing. Or I guess I can show that really quick. Just what this is. You see it down there, the LED's blinking. I told you it wasn't very exciting. But yeah. So that will give us enough emulation of that interface. And if we... In fact, this actually is probably going to be... The initial state is expecting all these to be... No, we'll just put 0 for that. So if I just do this, they should all go low. Why didn't this loop? It should definitely have still been running. Oh, why didn't it? I fear something might be wrong here. Whoops, that should be a macro. Actually, I want to make sure this is building right, so I'm going to make it tell me I failed. Okay. Yeah, I don't think this is running. Yo, world, exactly. This doesn't look like this is running to me. I'm just going to make sure I rebuild this. What is up with this? Should be fine. We're not getting any output. That's really odd. I'll even put this at the top. Is it not using this code for that? That would be stupid. But totally something that I would do. No, looks good there. Looks like our... This is very odd. Something very strange is happening here now. So this clearly works, calling the other one. Doesn't look like output works correctly from this. I'm going to put this in the ALU driver. This is very odd. So it definitely rebuilds. Okay, that worked. Just gonna try what I did from this other terminal. It's just running that program. What? Why am I getting 0 output from this? What is up with this terminal? I'm gonna restart that terminal. Because that was weird. Okay, so just to be sure here, if I do this, whoops. All right, yeah, I'm guessing that was also redirected somehow. Okay, so this is working now. Not too worried about high then. So we'll do make here again. Yeah, and now we get the invalid number of arguments. I'm just gonna do a cargo build here again. Good there. See if this redirected that. Good there. Try running both. Okay, same thing. Yo! All right. I don't know what the deal with that was, but it's working now. So you can see it's just sitting there looping and nothing is changing, which actually matches the test. This looks good actually, because if nothing happens, it doesn't like time out or anything. The test isn't written that well. It expects that the implementation is at least doing somewhat sensible things. We can test this actually by doing this. Check this out. We'll get rid of yo because we don't need it. But this will actually be kind of cool. If we say that the calibration failed, it should go into error state, and we should see the LEDs blink. Maybe not. I would have expected to. Oh yeah, I know why. Because we need to do fail here. Because it won't actually, like, the way I have this written in the test, it actually won't transition if like, it'll only transition if success or fail is asserted. If neither is asserted, it doesn't assume that's an error. I think that's fine. There we go. Hey, check that out. Our test is working, and it totally knows that this is wrong. This is so slow, you guys. By the way, this is not fast compared to the original one. That's so cool to see, though. So yeah, so this would be the same thing. Let me actually. I want to kind of show you guys how fast this is on hardware. And to do that, I'll just mess up the code. As long as the init is done, we'll just go straight to the error state. And I'll just build this in the background while we do other things. It's gonna take so long for this to run the whole test. This is about once per second. It looks like just looking at it visually compared to how fast the LEDs are blinking on the actual hardware, this is about 1/6 the speed. So it should take about 30 seconds to run a full test. Assuming that our actual implementation is not going to have much overhead. There might be some more optimization stuff that we can enable, parameters that we pass through Verilator that will become part of the flags for GCC. There might be just other parameters to play with, and that'll probably be worth doing. But I think I'm going to try to make it work before trying to make it faster. The count value, you mean like for the... Yeah, so it's running at 150 megahertz, and then this counts up to... where's my clock divider here? It's 1 shift left 24. Counts up to that. So if we know it counts up that much, and it's about 1 second, then this is how many clocks per second we're getting. And we can say divided by 150 million is low. Yeah, that's about 12% of the speed, and that's, yeah. Yes, it's running about 1/8 the actual speed. I mean, there's nothing here that it's really simulating, but yeah, it is going to be faster than at least a simulator that's doing more proper timing. This is just really testing the logic anyway. cool to see, though. And of course, this will get slower. Making hardware is not fast. That is just so cool to me, though, that this just to see this test actually producing output like this, even if we just gave it some trivial input, proves to me that this is at least a somewhat valid approach. So that's the LEDs. We actually do want to assert success, though, here. Yeah, that's also very true. 60 million clocks can simulate a ton of CPU. It won't simulate a ton in terms of audio and video output. But yeah, for a CPU, that'll be pretty good. Again, I'm pretty sure it'll get slower, but as our design grows, but it's definitely faster than Icarus or Model Sim. And only so because we can assume that the actual timing of the design is correct, which we might not actually be able to assume, but we're going to try and write the Verilog in a way that will allow us to hold that assumption. And I'll run this on the hardware again. We gotta do this crap again. All right. So just to compare here, I want to put this back. Fail like that. I'm gonna run this. Right, so that's about 1/8 the speed of those LEDs. So that's what you're seeing. But the fact that they're equivalent, that's the cool part. I love this. So yeah, I'm already just excited because this approach is somewhat already being validated. But now we actually want to do this properly. And to do that, I actually want to pull up Model Sim again. Because we're basically going to implement a state machine in Rust. Or Signal Tap, not Model Sim. That's what I wanted to pull up. I think actually the way that we use this bus currently, this never actually asserts that it's not ready, because we never fill up its internal queue, because we always just do a write and then a read and then a write and then a read. Or a read and then a write, rather. If we did like 10 reads in a row, then we might actually exhaust that. But the implementation should be ready for those signals. So I would like to assert them either randomly or pseudo-randomly or something, or maybe just with a specific pattern, so that just to make sure this thing will actually wait before sending too many commands. I should probably make a more sophisticated test, and the nice thing is that we can do that, and then just test it again in both environments. Still make sure things work. So, but this will be good enough to start with. I'm gonna be right back though. We'll see you guys in like 5 minutes. And I'm back. That left picture, it was one of the first FPGA projects I did is I did... so I call it hardware printf, but really it's putS. It would just print strings from the hardware to the UART. And I did that so that I could have... that was before I knew about things like signal tap. So I did that so I could more easily debug the hardware by actually printing out strings at different states. And that's the output of like doing a hello world or hello every week. So every weeks is a project I did for a while. I just recently stopped doing it, but a couple guys are still doing it. You can go to everyweeks.com. It's just a bunch of write-ups about what we would do on a weekly basis. So that's a screenshot from that. Hey, Mr. Tobe. Left one? Hold on, I gotta look at it. Yeah, that's the debug output before it worked. That was me debugging the UART implementation. It would just send out garbage because it didn't work initially. That stuff would have been really easy to debug with signal tap. But that's how it goes. That's a good point, Escape this. So what we want to do is we want to get an actual implementation of this memory interface. And at the moment, I'm not entirely sure the best way to go about this. Yeah, so now this just waits because it probably asserted a write, and then we just lost it because we're not watching for that stuff. In fact, if we look at the signal tap output, basically right after that happened, there was a cycle after, or a cycle on the cycle after that went high. We sent out our first write. But I think on the same cycle that it goes high, we need to be ready for that. So I will. Yeah, we'll just do it here. I'm a little bit worried about visibility. I'm wondering if I should actually set up the driver to dump traces now, as I know that Verilator can do that. And it kind of makes sense to just use that facility than to do it from Rust. So, thinking so at least. I'm actually just going to look at this. Because that will also kind of help us debug our implementation against this test. Verilator manual is a lovely piece of this kind of web design. Yeah, so it'll add waveform tracing code to the model. Verilator will generate additional whatever prefix trace CPP files that need to be compiled. In addition, Verilator or Verilator VCD sc.ccp for system C traces. Or this one must be compiled and linked in. If using the Verilator generate make files, these will be added to source targets for you. If you're not using the Verilator make files, Zucker1990, thanks for the follow. You'll need to add these to make file manually. That's fine. Having trace compiled in may result in some small performance losses. even when waveforms are not turned on during model execution. And okay, so for example, we could do just trace with a trace depth of 1, and that'd be fine. Yeah, our max width is 256. That should be totally fine. Okay. I was hoping too that you could do different formats here. I think I saw someone doing that at one point. I'm pretty sure they had an example with trace. That's why I'm looking down here. Actually, I'll just keep searching for trace. Yeah, here we go. It's in the FAQ. Tracers to varilator in your top level C code call varilated trace ever on true. Then you make a VCD object, and you call trace dump every time step, and finally call trace close. Yeah, so that doesn't look too bad. Okay, let's just see. I want to test this already because I want to see this work. Just go into our driver code here, and actually we'll go into our makefile first because we need to add the trace stuff. So our test driver. I think CC here defines the top, which is why we have that there. So I think we do like that. And we can just use the default stuff, see what happens. And then I'll do this stuff. In our driver, I don't know what this 99 thing here does. Let's just see what it says with the generated code. In fact, we'll do this. We'll do make here. And then we should be able to look at the generated code and see what that actually is. But first, we'll add this. Yeah, so we know everything works. We can initialize our module. Actually, before we initialize the module, we'll do this just in case that's a prerequisite. We know we can load the library and everything, so this is a good place to do this, I think. And we'll just do, you can just call this trace. I like to have the parens there. Actually, looks like this is definitely happening after it has the top, so we'll do this after this. I put 99 here, but I want to check what that is in a sec. And then, yeah. That'll be our trace file in the third argument. And then we can close the trace here. Yeah, we should also delete it. Because we did new here, right? Yeah. In fact, I don't really see why we couldn't do this. I think we are missing an include as well. Yeah, this is incomplete type. So we also need to include this. Now, I'm not sure if we need to add an include path for that. So we're gonna see. See if it output anything here. Probably didn't. It might be really annoying to add that actually. I'm pretty sure this is gonna have to be in my verilator directory, which I believe, oops. I can't remember where that goes. I think it's in share verilator, include. Yeah, it's this one. Although, actually, wait a minute. This is probably fine. Because it should add that to my include paths. Did I include the system C one? I sure did. Whoops. Nice. And then, so this will probably produce nothing in terms of output, like an empty trace. Oh yeah, this is this, no. This. Yeah, this needs to be a pointer, that's what it is. Two problems. Okay. Now this will complain, because I need to give it a trace file. I can just do trace.vcd. And I'm guessing this will not work. I'm guessing we'll get the trace file, but it's going to be empty. So actually, let's do ls here. And yep, there's our empty trace file. So we need to expose that update function. Forgot I have the file open 2 places here. So you have eval and final. And then what did they call it here? dump. So we can call this trace dump. All right, and okay, I actually need to call that on the trace as well, don't I? Okay. That means I also need to move the trace up here. And then down here we will do delete trace. And then we need to do a couple things. Expose that there. And then we need to implement it here. Let's actually trace. Oh, does it take a time parameter? Is that what that is? I still have that open? No, of course I didn't. I'm just gonna pull that up again. Okay, so UN64 is what I wanted to look at. That's fine, because we can just do this. That should make everything okay. At least in terms of building again. And then we'll expose that to the Rust stuff. Should be very easy here. So now we need to do some additional stuff here. We'll do let mute time is 0. And then what we can do is we'll do a dump here. Here. do one of these. Actually, let's do it here. I think this is okay. Really, though, I think I want this. Since this is where we're doing all our logic. Because it'll evaluate all that, and then we're going to change all of our logic. And then we're going to have to call eval again. It's actually here that I think we want this. Yeah, I think that makes the most sense. So then, this should be the same. And I can rebuild this. Let it sit for a minute. Now we got a bunch of data in our trace file. These things get big. And I'm fairly certain you don't have to use this same format. I'm pretty sure there's a better format for this, which is something we're going to want. Because I'm pretty sure VCD is text-based format. Yeah, that was 140 megs that just generated. Just the crazy thing. I think I have GTK wave here. Cool. Here's our traces. Now we haven't set the time scale, so it thinks it's all nanoseconds, and that's just crap. But I don't really care. So this is actually nice already. You can see here, a bunch of stuff happens. 100. It thinks it's nanoseconds, but again, it's not. This is where our init done is done, and then everything is a success. And then it tries to give us a write command here. But another thing that's happened here, and this is actually interesting. I'm glad I did this trace initially because I probably would have missed this. We never said that AVL is ready, and so when it starts doing this for the write, yeah, it shows the values because it knows the data widths. But yeah, so when it does the write, we actually have ready held low, and the way this interface works is if ready is low, that's basically telling whatever the interface is to stop what it's doing, and so it's just gonna sit here and hold, basically assert this write this entire time, until AVL ready is high. And that never happens. So this just sits there in that state. And the nice part is this is exactly what we wanted to see. So I'm pretty happy about that. Another thing that we can do here, we can, for the time being, instead of using a loop here, I want to use the loop here eventually, but we'll do this. Thousand cycles, just see what happens, and then just run this again. What? That should have. Oh no, that did work. Yeah, it just only showed let's change like that. We gotta do all this append crap again, but that's fine. That's pretty cool. Now, before I move on, I really want to know what that parameter was. This one. So that's actually on this object. Just looking for the trace function, which I assume would be that. Is that not here? Okay, it's probably find it in some very later header. Stop. Of course, it's not in there. I don't know where this function comes from. That's the issue here. I guess that'd be cool, diff param. Let's see if it's in here. Yeah, this is very late VCD again. VPI, isn't that the one? No, I don't think so. Yeah, here we can set the time unit. I don't really care about that though. Even though we totally know what it is. I can't remember. It was something LaRouche or something. Some guy did a how to make CPU in Verilog. I search on YouTube. Robert Baruch. He's got a video series like this, and somewhere he sits down with Verilator, and I'm fairly certain he had a different format that he was using for the traces. And it might not have been him either. I tried to find a couple of videos of this kind of thing at one point, and I just don't remember where they were. Yeah, it totally wasn't him. Some other video I saw. Yeah. Anyway, doesn't seem like the VCD is going to be an issue here. Since I'm not going to be saving these or putting them into Git or anything. It's just going to take up disk space. I don't really care about that. That's probably fine for now. But what was that other parameter? Bugs me that I don't know what that is. Yeah, VCD is ASCII. I'm just seeing, because I was pretty certain that I saw someone use Verilator and they had to output a binary format for that reason. But I don't know what it was. But I don't really care about that now. Where did I have that manual? Stuff flying all over the place. Here we go. Yeah, whatever. I'll just leave it. Doesn't seem to be important. We're getting what we need. One thing I always hated though about GTK Wave is that you had to do all this crap, append everything. But it's good enough for looking at this, I think. I think it's this tool is the one I want. Maybe not. Anyway. Or does GTK Wave... Can GTK Wave stay open? Or like watch the file or something? Let's just see. I don't think it does. Like if I just do this and just not have it open GTK Wave. Yeah, I can reload. Control-Shift-R. That's not too bad. I'll keep that open. Anyway. So a couple things here. The first thing that we're going to want to do, I want to assert that ready signal. I think we're going to need to make a state machine here. Let's do enum state. And so we can do, for example, idle. Let's do that first. And something like that. And if I just do this, yeah, a couple things changed here. So what happened now is that now we have this AVL ready signal, and that we assert that's high. So what happens here is two events, actually. I put my cursor in the middle of that. What happens is that this goes high, and then so the state machine in the test starts running, and it actually does two bursts here. The first one is a write, and then since we still hold that AVL is ready, then on the next cycle it says, okay, nothing to worry about. And it goes in and does the read as well. And then it will stay, because I think if we look at the write request and read request, yeah, here's the write request, here's the read request. Because AVL is still ready, it goes out of that state, but it's going to sit here and wait on that read until it comes back. Missing toggling clock. Good point, actually. That should be here. Oh, I'm not dumping the traces on the falling edges. That's what that is. I should do that. I should definitely be doing that. That's totally what that is. That should do it. The reason I'm doing this after my own changes here too is because these might cause some changes on this rising edge. Although maybe we want to catch that on the next edge, so it's probably actually best to do this. To do it here. Because we'll catch the outputs of this on the next rising edge. I think that is actually what we want here. Yeah, good call there. Because yeah, we definitely want to see those. There's our clock. And now everything's going to be twice as wide. So there we go. Much better. That's still fine. Right now the VCD is like 90K, just with how little things are changing at the moment. It was a 150 megabytes or something when I was just running in the infinite loop and I let it run for a few seconds, but now I just run 1,000 iterations, so not too bad. So yeah, here you can see that we just caught this AVL ready thing when the falling edge happened, just because of the way that we evaluate when we do those traces. It's going to happen in response to something else. For simplicity, I might move this back actually and have this here. I think that's going to make the easiest to read dumps, which I think is the most important thing here. Yeah, that I'd rather see. Oh, I'm getting hungry. Like, hungry enough that this might be a good break time. I think I'll get this. What have I done so far? This might actually be a decent stopping point now that we have all this up and running. That's what I'm thinking. To my other one. I think we'll do a couple things here. I think first of all, we can remove the trace. So we can do this. We can output a trace directory. Ah, cool. Yeah, it seems to do the trick at least. Very later, that is. I don't. The only thing that I still am uncomfortable about it is just due to me being unfamiliar. I just don't know where it breaks down. So I'm still a bit nervous about that, but so far it seems to be great. in terms of what we want here, which is faster iteration via simulation. But yeah, then I can do, just so I have the right commands here. And then, oops, this needs to open a different file. Nice. Yeah, I think this will definitely do the trick. Oh, yeah, and here's also the reload thing. But yeah, so if I do that, then we kind of know where these files are going. So what I think I'll do here, make a tracer as well. In our git ignore, we can ignore the traces. Then here, clean can remove the trace directory. And this is gonna sound really janky, because we're gonna change ALU tests like this to be DDR3 test, but that's actually what we want to describe here, because we are testing the DDR3 test thing. Although maybe that's not what I want to call this. Yeah, I'll actually probably just go with DDR3 test. They're probably fine. Also think these actually do need their suffixes here. If this were a real product, tests for the test files is something I would almost consider. Because these mistakes get expensive. Yeah, I think I'll set this up and then I'll head out for today. Even just getting a lot of this stuff set up is good progress, so I'm pretty pleased. Yeah, so we'll make the DDR3 test here as well when we do all. Test me the ALU test and the DDR3 test. So here we're going to do the DDR3 test driver, DDR3 test. I don't know if we'll do it, if we'll actually do an ALU test. Episode 3 is probably going to be more of this, actually implementing this memory interface. So kind of coming with that two-pronged attack. So I guess that would be what would be in episode 3. And I don't know when that would be. It's going to be pretty random, I think. Worst case next Sunday, I bet, but probably next weekend. I'm not sure. This also, we want to make a trace file here. 3 trace is going to be tracer. Let's do your 3test.vcd. Currently I'm using an underscore. That's fine. And yeah, and then this becomes DDR3 trace. And now we should be able to do. Oh, thanks so much for the sub, Defram. Really appreciate it. I didn't think you'd get much out of this. That makes me feel good. By the way, DDR3 tests should rely on the driver. Yeah, it needs to be test driver. I should build stuff, and it should also run it. No, make test will run it. And it looked like it did. Cool. File date's correct. I'm still not convinced, though, that Verilator generates makefiles that have proper inputs. So that's kind of annoying, but I mean, really the only consequence is that it takes a little while longer to build, and that's not really that. This isn't really where the bottleneck's going to be. But yeah, so here we got the outputs of the test here. I love that this is working. Maybe we actually don't need these .dlls here, which I would like not to have. I think that actually worked fine. Seems to be okay here at least. Cool. Just gonna add all and make sure we're okay. Looks great. Current branch appears to be broken. Really? Does appear to be broken because this is a lot of changes. This is really weird. What happened here? Git! Alright, here's what I think I'm going to do. The easiest way that I know to fix this kind of thing is I'm just going to copy the directory. And we're going to do this. Close GTK wave because that'll be file watching. Remove it. Git clone git at github.com. Yep. Ferris. xenowing.git. I'm happy to hear that, SK test. Because I enjoy doing this stuff, so I'm very happy if you guys enjoy hanging out and stuff. Oh, yeah. Okay, this looks much more sane at least. Yeah. Okay, I don't know what happened. But this looks good. I'll come up. The Ferris sphere is nothing, not even hardware. More like not even Git. I mean, I think this is going relatively well so far. Slowly but surely, we are making some progress. World of Eden's Art, thanks for the follow. I'm happy to hear that, Iron Codes. It's all stuff you might have learned in school, but that does make me really happy because I like doing these streams. It's stuff I want to do anyway. So it makes me happy that you guys enjoy it. That it's worth putting forth that extra little bit of effort to put it on stream. So now I'm just going to do make clean and just test that all of that is okay. Because I think we're actually missing one here. Just that we want to do... Oh yeah, all these files are wrong now. Ugh. Because I deleted that directory. Ew. Don't like when we have to do this crap. But sometimes it happens. Okay, yeah. So our make file should also clean the the other Rust project. I'll just force push this. I would love to watch you stream, DevPram. That would be awesome. I think you guys are learning a lot from me. DevPram streams would be awesome. My streaming gear. So I have a pretty cheap webcam that I use. I actually have two webcams now. I have a much nicer one that I actually don't use for my face. I bought it so that I could use that for my face and use the cheap one for looking into my Virtual Boy when I was doing hardware testing, but it wasn't high resolution enough. So I had to use the nice one for that, and I have it on off to the side because I have it at really crazy like exposure parameters and stuff, so that when it's looking in the Virtual Boy, it actually looks clear. Which is also why I don't want to like keep moving stuff around because I don't want to change all those settings. Anyway, so I have that. I run just everything off my main PC. And I just use OBS, and I have several scene collections for different things that I stream, and then all my overlays are just Photoshop files and PNGs. So whenever I do a new stream, I just copy the folder and then change all the stuff in the PSDs, export the PNGs, and then bring it back into my OBS setup. It's pretty easy actually. So in terms of hardware, that's about it, and that's most of my workflow. The annoying things about doing this stream though are to remember to talk a lot, which I guess kind of just comes natural when I feel like people are watching. So I kind of do that. And then deciding to set up all the little things like, oh, when I stream, I'm going to start streaming and then wait 5 minutes and then start recording, start doing the thing. I say the intro because that gets myself in kind of the mood. And then I have to have this big dumb looking font size, which is not something I end up thinking about while I'm doing it, but it's something that annoys me every time I start. But it's fine. Oh yeah, and actually, now that you mention it, Ion Codes, I do have a nice mic. It's a Shure SM7B. These things are this is the Michael Jackson mic, and I've got a mic arm for that. This is probably the most expensive piece of gear that I have. And I don't think you need it. If you see my very first streams, that was actually just using the microphone on like the Mac earbuds, like this little guy, and that was okay. I didn't buy this mic until, so I started streaming early 2016, and I streamed kind of off and on, and then I stopped streaming for a while I moved back to Norway and got my life kind of set up again. And then when I started streaming again, I decided that I was going to commit to it because I knew I had an audience. I knew that I would enjoy it. And so at that point, I bought the new mic. So yeah, that is that's the more expensive part of my gear. If you see me wearing headphones, I'm usually listening to music. I guess the headphones count as part of the gear, but like I don't have my mic going through my headphones or anything because that would annoy the hell out of me. Dark Second, does Rust compile to risc-v? Yeah, there is a toolchain for risc-v. I haven't checked that out though, because I'm fairly certain. I don't think there are full built Rust compilers for risc-v. If there is, I should look into using that. Apparently it was upstreamed. Tizio, thanks for the sub. Appreciate it. I will Google that, codes. Unfortunately, not for long, Pyro. I think I'm gonna head out soon, but hey, here's this risc-v quick start thing. I assume this is what you were pointing out, Iron Codes. So yeah, I guess you build the toolchain locally, and then yeah, this is the quick start. That's pretty cool. I might check that out. I was expecting to use C just because I think that having to use these build chains that are kind of in flight isn't the most comfortable thing, but I would love to code for my own hardware using Rust. That'd be pretty sick. Although it would be bare metal Rust, but it's not like that's much worse than bare metal C. Tends to be a little bit more verbose at the lowest levels, but the rest is quite nice. Anyway, I think I'm going to head out. Thanks guys again for hanging out. And thanks for the new subs. Appreciate that. I don't know when the next time I'll be streaming this hardware stuff is. I might try to sprinkle it throughout the week because I know I want to work on this stuff, but we'll have to see how it goes. Worst case, it's next weekend probably. Anyway, thanks again, guys, and I'll see you next time.